welcome you in the lecture series of Basics of Communication Engineering. It is 14th lecture of this series. In previous lecture, we have discussed about generalized concept of angle modulation. In this lecture, I would like to discuss about properties of angle modulated wave and difference and comparison between FM and PM, and also we will discuss about the types of FM, narrowband FM and wideband FM. And the outline of this lecture are properties of angle modulated wave, difference and comparison between FM and PM, relationship between FM and PM, and types of FM. In the objective of this lecture, you will able to explain the different properties of angle modulated wave, and you can also explain how can you generate FM using phase modulator and how can you generate PM using frequency modulator, the bandwidth of FM wave, and the basic concept of narrowband and broadband FM. So first of all, we will discuss about properties of angle modulated wave. The first property is consistency of a transmitted signal, means the transmitted signal will be consistent here. If this is a carrier wave and this is modulating signal, and from the previous lecture, the AM wave where the amplitude of the carrier is changed in according to the modulating signal. So here the amplitude is going to change, and in PM when the modulating signal goes from positive to negative, from negative to positive, there is minimum frequency or frequency is stretched. When the modulating signal is going from negative to positive, then there is frequency is compressed. At this case means phase is lead. In this case this is PM wave. And in frequency modulation in FM wave, when the modulating signal having the highest value, then at this point frequency will be maximum, and at the point where the modulating signal having the lowest value, then there will be the minimum frequency. So these are the AM, PM and FM waves. You know about these. We know PM wave can be expressed as XCPT. It is AC cos 2 pi FCT plus KP XT, where XT is the modulating signal, KP is the phase sensitivity, and AC is the amplitude of the PM wave. This is equal to the amplitude of the carrier wave. And this XCPT, it is the FM wave. And we also know the FM wave can be expressed as XCFT. It is AC cos 2 pi FCT plus 2 pi KF integration 0 to T x tau d tau. And here this term accounts for increase or decrease in the instantaneous phase theta due to message signal xt. And here Kf is the frequency sensitivity. And from these two equations, you can see that the amplitude of the FM or PM wave is maintained at constant value equal to the carrier amplitude AC for all time, irrespective of the sensitivity factor Kp and Kf. So the average transmitted power of a angle modulated wave, it will be constant, and it will be P transmitted or radiated wave. So the average transmitted power PTAV, it is AC square by 2 RL. And if I consider the load resistance RL is equal to 1 ohm, then the average transmitted power, it will be 1 by 2 AC square. So you can see it will always be consistent with the amplitude of the carrier wave AC. Now the next property is non-linearity of the modulation process. This is another distinctive property of the angle modulation. It is non-linear characteristic because both PM and FM wave violates the principle of superposition. For example, suppose that message signal xt is made up of two different components x1t and x2t, or you can say xt is the composite signal that is made from two signal x1t and x2t. And if I consider XCPT, XCP-T, XCP-T are PM waves produced by XT, X1T and X2T. This means the XCPT is produced by the modulating signal XT, XCP-T it is produced by the modulating signal X1T, and XCP-T it is produced by the modulating signal X2T. So the PM wave that is produced by the xt, it can be represented as xcpt ac cos 2 pi fct plus kp xt, but xt is equal to x1t plus x2t, so I can write kp x1t plus x2t. And the PM wave that is produced by X1T, it is CP-T, it is AC cos 2 pi FCT plus KP X1T, and the PM wave produced by X2T, it is XCP-T, it is AC cos 2 pi FCT plus KP X2T. So from this equation, we can see that the principle of a superposition is violated, because here xcpt not equal to xcp-t plus xcp-t, but xt it is equal to x1t plus x2t. So you can see the input, it is if I consider this is one system, the input xt, if it is combined as x1t plus x2t, but output it is not combined of y1t plus y2t. So we can say that this is a non-linear. So there is a this is non-linearity of the modulation process here in PM wave, or you can say in FM wave. So PM wave is known as linear modulation, and similarly you can get the FM wave is non-linear process. Now third property, irregularity of zero crossing. Since theta t depends on the message signal xt, as theta t is equal to 2 pi fct plus kp xt, or you can say 2 pi fct plus 2 pi kf 0 to t x tau d tau. This is theta t for the phase modulation, and this is theta t for the frequency modulation. From this equation we can say that the zero crossing of FM and PM wave will not have a perfect regularity in the spacing between the zero crossings. Zero crossings are defined as the instant of time at which the wave changes its amplitude from positive to negative value. So spacing between the adjacent zero crossing will not constant, instead it will keep changing constantly. And we can see that here that the spacing between zero crossing is going to change here. So it is constantly changing, and the spacing between zero crossing, and we can see that this is one of the important difference between angle modulation and amplitude modulation. Now property fifth, visualization difficulty of a message waveform. In AM, we can see that message signal is the envelope of the modulated wave. In this is not so in angle modulation. Just you have seen in the figure of phase modulation and frequency modulation. In general, there is a difficulty in visualizing the message signal in angle modulated wave. Just like in this figure in AM, we can easily visualize the modulating signal or baseband signal will be the envelope of this. But in PM and FM, it cannot be easily visualized what will be the shape of your modulating signal. So there is a difficulty. And we have shown that in previous lecture that the PM wave can be plotted using the differentiated version of xt, that is dx by dt, as a modulating signal. So if I'm going to take the differentiation first of my modulating signal, then I'm going for the frequency modulation, then the output from the frequency modulator, it will be the phase modulated wave. So if I compare these two, frequency modulation and phase modulation, in frequency modulation I am going to take the modulating signal as it is, and this is given to the phase frequency modulator, then it will be the FM wave. But in PM, if I will take the d by dt xt means differentiation of the modulating signal, and now if I will do the frequency modulation, then the wave it will be PM wave. So there is difference in the modulating signal in PM and FM. So there is very difficulty to visualize the baseband signal or message signal in PM and FM. Now, property fifth, trade-off of increased transmission bandwidth for improved noise performance. An important advantage of angle modulation over amplitude modulation is the realization of improved noise performance. The improved noise is performed, however, at the expense of increased transmission bandwidth of angle modulation. Such a trade-off is not possible with amplitude modulation, since the transmission bandwidth of amplitude modulated wave is fixed, and that is 2 FM. Now we will discuss the difference between FM and PM. So here you can see the maximum deviation point in frequency modulation, and the maximum deviation points in the frequency modulation are the peak values of the modulating signal. So at the highest value of the modulating signal, there will be a high frequency in the FM wave, and at the minimum value of the modulating signal, at this point there will be minimum frequency in the frequency modulated wave. So these are the maximum frequency deviation point in the FM wave, and on the other hand the maximum deviation point in PM wave are different. The maximum frequency deviation point are the zero crossing point, means if I am going from negative to positive, then at this point in the PM wave there will be high frequency, and if I am going or modulating signal is going from positive to negative, so in this at this point in there is minimum frequency. So the frequency deviation points are different from the FM wave in PM wave, and also the here maximum value of the modulating signal, there is a maximum phase deviation. So here we have seen that the maximum frequency deviation FM occurs at the point corresponding to peak values of modulating signal, but in PM the maximum frequency deviation occur at the point where the rate of change of modulating signal is maximum, means near to zero crossing point of the modulating signal. So although the phase modulation produce FM, the maximum deviation occurs at different points of the modulating signal. In PM, at the peak amplitude points of the modulating signal, the maximum phase deviation occurs. So these are the key points in difference between FM and PM. Now another difference is the effect of modulating frequency. In FM, the frequency deviation is proportional only to the amplitude of the modulating signal, means del f is equal to kf into am, and it is independent of the frequency FM. But in PM, as the modulating frequency is changed, the rate of change of modulating voltage changes. This change the frequency deviation. So in PM, the frequency deviation increase with increase the modulating frequency FM, and decrease with decrease the modulating signal. So in PM, the carrier frequency deviation is proportional to both modulating frequency and amplitude, whereas in FM the carrier frequency deviation is proportional only to the amplitude of the modulating signal. Now if I go for the comparison between FM and PM system, we can see for the FM wave we have the mathematical representation of the equation as XCFT. It is AC cos 2 pi FCT plus MF sin 2 pi FMT. MF is the modulation index, and in the phase modulation, and the PM wave can be expressed as XCPT. It is AC cos 2 pi FCT plus MP cos 2 pi FMT. MP here it is the modulation index, and in FM wave frequency deviation is proportional to the modulating voltage only, and the PM wave the phase deviation is proportional to the modulating voltage. Here the frequency deviation is proportional and here the phase deviation is proportional. And in FM wave associated with the change in the FC, there will be some phase change, and PM wave associated with the change in phase, there is some change in FC, carrier frequency. And in FM, frequency deviation is proportional only to the modulating voltage, and in PM the frequency deviation is proportional to the modulating amplitude as well as modulating frequency FM. And in FM, noise immunity is better than AM and PM, and in PM noise immunity is better than AM but worse than the FM, or but less than FM. And in FM, signal to noise ratio is better than of PM, and in PM, signal to noise ratio is inferior to that of FM. And FM is widely used. PM is used in some mobile systems. PM is used in some mobile systems, and in FM the modulation index, it will be equal to frequency deviation divided by the frequency of the modulating signal, means del F by FM, or you can write it as KF AM by FM, and this is proportional to the modulating amplitude as well as modulating frequency. And in PM wave the modulation index is equal to Kp into AM, so the modulation index is proportional only to the modulating voltage in PM. Now, relationship between FM and PM. We know the expression for FM and PM wave in time domain. It is for FM, it is AC cos 2 pi fct plus kp xt, and in FM it is AC cos 2 pi fct plus 2 pi kf integration xt dt. So, comparing these expressions, we can conclude that FM is exactly as PM and having a modulating signal integration xt dt. So instead of here xt, so here we can have the FM is a PM, but the modulating signal, it will be integrated version of the modulating signal instead of the signal xt. This means that we can generate FM wave by applying the integrated version of xt to the phase modulator, because FM is basically PM. So here in this figure you can see we are just integrate the modulating signal first, and then we will apply to the phase modulator, and this will give you the FM wave. And this is the carrier oscillator that will generate the carrier AC cos 2 pi fct. And similarly, we know these two equations for PM and FM wave, and from these two equations we can also say that PM wave is actually FM wave having modulating signal dx by dt instead of xt. So if I consider the PM wave is actually FM wave, but here the modulating signal is d by dt xt instead of xt. So modulating signal is first passed through the differentiator and then applied to the frequency modulator. As you can see in this figure, the modulating signal, baseband signal, is applied to the differentiator, and then this signal is now the modulating signal for the frequency modulator, but now this signal give you the PM wave xcpt. So at the output of a differentiator you have dx by dt, and at the output of frequency modulator you will have PM wave. So the output of frequency modulator, here it will be xcft at this point. So at this point the output, it will be AC cos 2 pi fct plus 2 pi kf, because you are using frequency modulator, you have 2 pi kf, and the modulating signal, it is integration. In equation of FM you can see there is integration of the modulating signal, so you will have this kind of equation. And we can write this equation as AC cos 2 pi fct plus 2 pi kf, and this will be xt. And you can see, if here I write 2 pi kf is equal to kp, So I will get this FM wave will be equal to the PM wave AC cos 2 pi FCT plus KP XT. So you can see that FM wave will be the PM wave. So here I did the frequency modulation, and this FM wave it will be equal to PM wave. So likewise, you can see that the PM wave will be FM wave if I am having the modulating signal is the integrated version of the modulating signal. So now we will discuss types of FM. Depending on the value of frequency sensitivity KF, FM can be divided into two types: narrowband FM and wideband or broadband FM. So narrowband FM. A narrowband FM is the FM wave with a small bandwidth. So they are having the smaller bandwidth, and this system is used in FM mobile communication such as police, wireless, ambulance, taxi cabs, etc. And the modulation index of a narrowband FM is small as compared to 1 radian. So the modulation index will be less than 1. So if the modulation index is less than 1 in FM, then we can say that this is the narrowband FM. And we know that the angle modulated signal can be represented as AC cos 2 pi FCT plus theta t, where theta t is 2 pi kf integration x tau d tau for FM wave. And so we can write the FM wave, it will be AC cos 2 pi FCT, and so it will be cos A plus B cos A cos B minus sin A sin B. So from here I can have this equation as AC cos 2 pi FCT cos theta t minus sin 2 pi FCT sin theta t. And if theta t is small, then let theta t less than equal to 0.2 radian, then cos theta t it will be equal to 1, and sin theta t will be equal to theta t. So the narrowband equation can be represented as by putting this value in this equation 8. We will have FCT, XCFT, AC cos 2 pi FCT minus theta t sin 2 pi FCT. Since theta t is 2 pi kf integration x tau d tau, so we can have it as 2 pi kf am cos 2 pi fmt dt integration of this, because if I consider xt is am cos 2 pi fmt, here we can have kf am by fm, and if I will take the integration of this, so it will be sine 2 pi fmt by 2 pi fm, and 2 pi cancel by 2 pi, so we will have only fm here, and so it will be mf sine 2 pi fmt. So it will be mf sine 2 pi fmt, and here mf is the modulation index, kf am by fm, and the maximum permissible frequency deviation del f kf into am, it is restricted to about 5 kilohertz. So the frequency deviation, it is restricted to 5 kilohertz in narrowband fm. Now this is equation 9 we have solved here, and we can write this equation as AC cos 2 pi FCT plus AC by 2 MF cos 2 pi FC plus FMT minus cos 2 pi FC minus FMT, or we can write it as AC cos 2 pi FCT plus MF AC by 2 cos 2 pi FC plus FMT minus MF AC by 2 cos 2 pi fc minus fmt. And this first part is the carrier, and this part is the upper sideband, and this is the lower sideband. Here the negative sign associated with the lower sideband represent a phase shift of 180 degree here, this negative sign. So in this spectrum we have shown that there is 180 degree phase shift in the lower sideband. Upper sideband is at fc plus fm, and lower sideband is at fc minus fm, and the carrier having the frequency fc by 2. So if I will take the Fourier transform of this, then I will get AC by 2, and the impulse at this frequency fc. So it is the amplitude of the carrier it is AC by 2 in the frequency domain, and the carrier and the amplitude of your sidebands, it is AC MF by 4. You can find out these amplitude by taking the Fourier transform of this equation. And here you can see the bandwidth is 2 FM, means the bandwidth of a narrow band FM is same as AM wave, amplitude modulated wave, 2 FM. Now we will discuss broadband FM or wideband FM. The wideband FM wave has infinite bandwidth and hence known as wideband. The modulation index of wideband FM is higher than 1. So if the modulation index you calculate of angle modulation or FM wave, if it is greater than 1, then we can say that this is wideband FM, and the maximum permissible frequency deviation del f kf into m is 75 kilohertz, and it is used in the entertainment broadcasting applications such as FM radio and etc. Theoretically, the bandwidth of FM wave is infinite, but practically it is calculated based on how many sidebands have significant amplitude. The simplest method to calculate the bandwidth, it is 2 FM into number of significant sidebands. With increase in modulation index, the number of significant sidebands increased, and this will increase the bandwidth. The second method to find the practical bandwidth is a rule of thumb or Carson's rule. It states that the bandwidth of FM wave is twice the sum of the deviation and the highest modulating frequency. So it is bandwidth is equal to 2 del f plus FM, and this Carson's rule gives correct result if the modulation index is greater than 6. Now we will go for the comparison between wideband and narrowband. The modulation index for wideband is greater than 1, and for narrowband the modulation index is less than or slightly greater than 1, and but in this case it will be very greater than 1, 2, 5, 6, 8, 10, anything. And the maximum deviation in the wideband, it is 75 kilohertz, and in narrowband it is 5 kilohertz. And the range of modulating frequency in wideband, it is 30 hertz to 15 kilohertz, and in narrowband the range is 30 hertz to only 3 kilohertz. And the bandwidth of wideband FM large, and it is 15 times higher bandwidth of the narrowband FM. So it is 15 times higher than the narrowband FM, and in narrowband FM this is approximately same as that of amplitude modulated signal AM, and this is equal to 2 FM. And in application, the wideband are used in entertainment broadcasting and can be used for high quality music transmission, and in narrowband FM they are used in FM mobile communication like police, wireless, ambulance, etc. And this is used for speech transmission and pre-emphasize and de-emphasize circuits. But here we will require for both the wideband FM and narrowband FM, there is be a requirement of pre-emphasize and de-emphasize circuit at the transmitter and at the receiver side. So this is the end of this lecture. Here we have discussed about properties of angle modulated wave, difference and comparison between FM and PM, and also type of FM. This was 14th lecture of the lecture series of Basics of Communication Engineering. In the next lecture, we will discuss about generation of FM waves. Till then, thanks for listening this lecture. Thank you.